Hi everybody, welcome back to chapter 11. This is section 4, and in section 4 we're going to talk about how adding a solute to a solvent affects its vapor pressure. So I think before we do that, we have to talk about what the heck vapor pressure is and the different types of solutes that you can add. So when you have a closed container and you have a liquid in a closed container, that liquid evaporates, and the liquid molecules, well, the gas molecules of that substance stay trapped inside the container and bounce around. And as they bounce around, they exert pressure on the walls of their container. And that pressure that the gas above the liquid exerts on the walls of its container is known as vapor pressure. So not only do we have water vapor in here from the water of the soda evaporating, but there's also air in here. So there's also oxygen and nitrogen gas molecules bouncing around and exerting pressure on the walls of their container. The pressure that a gas exerts on the walls of its container in a closed container above the surface of a liquid is called vapor pressure. Okay? Now, when you add stuff to a solvent, like that soda, it will affect the vapor pressure. And we need to know how. So it depends on the stuff that you add as to how it affects the vapor pressure. Sugar and salt and, any ionic compound basically, those are what we call non-volatile solutes. A non-volatile solute is one that does not itself evaporate easily. It's one that has a low vapor pressure itself. So a non-volatile solute will not evaporate. And those are the common things that you add to water, like sugars and salt. Okay? Volatile solutes do evaporate easily, and those would be things like ammonia or alcohol or acetone, and we'll talk about those later. But so for now, we're going to talk about what happens when you add salt to water. What does that do to water's vapor pressure? Well, pure water has a particular vapor pressure depending on the temperature that it's at. The higher the temperature, the greater the vapor pressure. Let me show you represent a graph, a table that gives you the vapor pressures of water at different temperatures. Hold on one second. So this is from Oklahoma State Education Department, and you can see that as the temperature of water increases, as it goes from 0 to whatever, the pressure, the vapor pressure of water above it also increases. You can see over here at 56 degrees, it goes up to 123. And this table goes longer, but I want you to understand, and it makes sense, that the hotter your water is, the greater the rate of evaporation. So you're going to generate more water molecules. And so therefore it would exert greater pressure on the walls of its container. So the higher the temperature, the more gas you create, which creates a greater vapor pressure. So when you add salt to water, okay, so let's just kind of diagram it. Here's pure water. Let's make this a closed container, okay? Here's pure water. Only surface molecules can evaporate, and as those surface molecules evaporate, they exert vapor pressure, and that's a constant for that any given temperature. Now, if you put salt or any other non-volatile solute in the container, not only do you have those water molecules on the surface, right, but you also have your solute molecules on the surface. And remember, there's an attraction between the solute and the solvent. The water surrounds the solute and is attracted to it. And so you can think of the solute sort of as an anchor. It attracts the water in the solution and limits its evaporation. And so if you get less evaporation, you still will get, I made a solute molecule evaporate, not cool. If you get less evaporation, you get less gas. And if you get less gas, you get less vapor pressure. So the general statement that can be made is when you add a non-volatile solute to a solvent, it will lower the vapor pressure of the solution. So the vapor pressure of this solution will be less than the vapor pressure of the pure solvent. And that is known as Raoult's law, okay? And we'll be performing calculations and quantifying that in just a moment. This question was on an AP exam not long ago. I hope it's in your notes. I hope that you can see it. You have a closed system. This is encased. And in the beaker here on the left, you have pure water. And in the beaker here on the right, you have a solution, salt water, whatever, okay? So this is pure water. This is like salt water. Now, I already told you that salt water will have a lower vapor pressure than the pure water, okay? Over time, so going from A to B, time has passed. What you'll notice, if you were to actually do this experiment, is that water leaves the pure water beaker and goes into the aqueous solution beaker. And the question becomes, or the question was on the AP exam, why does that happen? Why would water leave this beaker and enter that beaker? So take a minute to think about that. In nature, there's always a drive toward equal, okay? Like think of diffusion. Things move from a region of high concentration to low concentration until they're the same concentration. Think heat flow. Heat flows from high to low until things are the same temperature. This is a similar concept. This pressure is higher than this vapor pressure. So in an attempt to equalize those vapor pressures, water will leave this solution and enter that. Because if water leaves this solution and enter that, then you have more liquid water which can evaporate and equalize the vapor pressures. But it'll never happen because you'll never get rid of the anchors, right? So all the water leaves in an attempt to equalize the vapor pressures. So the vapor pressure above the solution is less than the vapor pressure above the solvent. So water will move into the solution in an attempt to equalize the vapor pressures, though that will never happen, okay? So the summarizing overriding principle is that when you have a non-volatile solute, you will lower the vapor pressure of the solvent. So solutions, the vapor pressure of a solution made with a non-volatile solute will always be less than the vapor pressure of the pure solvent. How much less, do you think? How much less? Depends. How many anchors do you put in the water? So the greater the concentration of your solution, the lower the vapor pressure will be, the greater this effect will be. So we're going to quantitate it. And this reaction that we use, the reaction that we use to quantitate it is called Raoult's law. And here's the equation, maybe, if it works. Oh, look at that. The pressure of the solution, this is pressure or vapor pressure, right? It's the same thing, is equal to the mole fraction of the solvent. I'm telling you, it's the mole fraction of the solvent times the pure pressure of the solvent. This is the pure vapor pressure. For example, I guess I should pause. Mole fraction has no units. It's unitless, right? The vapor pressure can be in any unit, but they have to be in the same unit. So this can be in atmospheres or millimeters of mercury or pascals or kilopascals, PSI, it doesn't matter. But these two pressures have to be in the same unit. And usually they will be. Oh, another unit you often get here is torr. Torr is the same thing as millimeters of mercury. All right, So calculate the expected vapor pressure at 25 degrees for a solution prepared by dissolving 158 grams of common table sugar in 643.5 mils of water. At 25 degrees, the density of water is 0.9971 grams per mil. Tony, this is what I was referring to. If they give you a density of water at a different temperature, go with that. Don't go with 1, okay? And the vapor pressure is 23.726 torr. All right, let's get some of these numbers down. We know our temperature, we're at 25 degrees, okay? We have 158 grams of sugar, sucrose. And they gave us the molar mass of sucrose. Why would they give us the molar mass and the grams of sucrose, do you think? What could you find if you had the grams and the molar mass of sucrose? Moles, right, you could find moles. So you could divide that by the formula mass. One mole is 342.3 grams, and you could get the number of moles. So 158 divided by 342.3, and that gives you 0.46, let's say 2 moles of sucrose that we're putting in our water. We have 643, I think it was 643.5 milliliters of water. And we have the density of water. If you have the volume of water and you have the density of water, you can find the grams of water, because density equals mass over volume. So mass equals density times volume. The density, 0.9971 grams per mil. The volume is 643.5 mils. So I can multiply those, 0.9971 times 643.5, to get the mass of water, 641.634 grams of water. And if you have the mass of water, you can find the moles of water. Now, why would I need the moles of solute and the moles of solvent? So I can get the mole fraction. That's why, right? That's why I'm going through all this, so I can get the mole fraction. So we're going to take this, our answer, and divide it by the formula mass of water, right? 1 mole is 18.02 grams. And if you divide those, you get 35.61 moles of water. So now I can get the mole fraction of my solvent. Actually, I could just solve this whole stinking thing if we want to. Do we have any other numbers? I got sidetracked. They have the vapor pressure of water to be 23.76. That's the other given number. And what they're asking us for is the vapor pressure of the solution. Okay? So what we will do is we will take our Raoult's law, the vapor pressure of the solution equals the mole fraction of the solvent times the pressure of the solvent. We must first get the mole fraction. So in order to get the mole fraction of the solvent, I'll put the moles of the solvent, 35.61, over the total moles, which is going to be 35.61 plus, how many moles of solute did we have up there? 0.462? And then we'll multiply that number by the pure pressure of our solvent, which is 23.76 torr. Okay, so what I did is I solved for my mole fraction of solvent. I took this and divided it by the total, and I got 0.9872. That's 0.9872. And I multiplied that by the pressure of my solvent. And I got the pressure of the solution to be 23.4. Remember, we said it should be lower. If it was pure water, it would have been 23.76, but due to the anchors holding it down, it's lower. Have a great night.